All right. So basically, what we have learned last Friday, before we end our um, lecture, was we look at the eutectic system. We have looked at the eutectic system. So what does it mean by eutectic system? It means that eutectic itself, it means that the alloys produced is basically having a low melting temperature. Binary, it means that you have two elements mixed together. So the terms binary eutectic literally explain or define as the two elements that mix together to form a low melting temperature alloys. So if you still remember why it is possible for eutectic system to establish, is because it didn't follow the Hume rotary rules. So if let's say that it forms isomorphous system, it means that these two elements actually follow the Hume rotary rules, and after that it will actually form a homogeneous system. Meanwhile, if it didn't follow the Hume rotary rules, so what happened is that it will form the so-called eutectic system, right? So this has not been included in your lecture notes, this additional notes, but I believe something that you can look at from your e-learning. Okay, so we have a few examples for eutectic system. I think literally we have looked at copper silver and also lead tin. So most of this sample or most of this alloys basically been used for soldering materials. Okay, so we have also another examples for eutectic system, which has iron carbon or cast iron phase diagram. We are going to look at iron carbon phase diagram perhaps after we finish with binary eutectic, because it also contains not only eutectic but also eutectoid system. Okay, and there's also another examples of aluminium silicon phase diagram. Okay, so the essence of eutectic system, as I told you, the reaction is basically a liquid. When it solidify, okay, when it solidify, it forms another two solids, which also known as alpha and beta. Okay, so this equation is a very famous equation to explain the eutectic process. Okay, so that is why over here you will see that eutectic reaction, it has liquid, okay, a double head arrow that explains the heating process. Okay, if you have two solids, when you heat it together, it forms one liquid, but a solid that you cool it, okay, it will form another two solids, alpha and beta. So this is actually uh, the, uh, the key for eutectic system. And in order to write a full eutectic equation, it is important to write the composition as well. So basically, you can see over here, liquid with a composition of eutectic, okay, double head arrow, alpha, composition of C alpha plus with beta, C beta. And this, I think, I've explained also in your last lecture. And perhaps those who have not looked at the lecture, you can see it. It is available in the YouTube, right? So this is basically the examples of eutectic phase diagram. So you have the temperature on the y-axis and also the composition, the x-axis. Okay, so this is basically a copper silver eutectic system, but more or less for any eutectic phase diagram, the phase diagram will resemble almost the same pattern. Eh? You have like on your left hand side where you have alpha, and on your right hand side you have beta. So alpha and beta, it means that the phase exists as a soul or as an individual element. So you have like more pure alpha on your left hand side and more pure beta on your right hand side. On the top, of course, at higher temperature will be exist as liquid, and in between you have the mixture of these two elements. Like for example, if liquid it's been bordered with alpha, so you have alpha plus beta. Okay, and if the liquid is a border to beta, then you have beta with liquid. So that is why over here you also have a so-called liquidus line and solidus line. Okay, so the invariant point, the line, the horizontal line that you see over here is actually known as invariant point, where this is actually the eutectic temperature or the eutectic point. So if I ask you what will be the melting temperature of this eutectic alloys, you can literally read it as 779. It is mentioned normally in the phase diagram over here. You see 779. So this is actually the eutectic temperature. Okay, and the point that intersect between the liquidus line and the solidus line, okay, is known as the composition of eutectic. So CE, so 71.9. Okay, the intersection between the invariant point or the eutectic line to the solidus line of alpha, you have this one, C alpha, which is equals at 8%, and another N, which overlap or intercept at solidus line of beta. Okay, also we give the composition of eutectic for beta, which is 91.2. Okay, and I have to tell you that when you actually extrapolating the data from the phase diagram, most of the value is actually been told or written in the phase diagram. So you don't have to read it manually by yourself. If let's say that I will ask you what would be the temperature of the eutectic, so if you read it literally, maybe you get 700 something, but the more accurate value will be mentioned here. So it is around 779. Okay, the same thing for the composition of alpha. Okay, if you drag it from here, you will get like around 10. But I think the more accurate value is around 8. And then over here, you get 70 something, which will be more accurate at around 71.9. And still, for beta, if you drag it over here, you will get at 90 plus. So it will be like 91.2. Right. So I've actually explained all these terms on the invariant point in the last lecture. We have also seen the reaction or the key reaction for eutectic. Okay, and in order to write a full equation, you will have like liquid with the composition of eutectic. Just now, I think the point of the total intersection of solidus line and liquidus line is at 71.9% of silver. Okay, double head arrow of cooling and also heating. So we get alpha at around C alpha 8% and plus beta at composition of beta at around 91.2. Right? Okay, so we also have seen this. We have a few composition of phases in the binary eutectic system. You have alpha on your left hand side, beta on your right hand side, liquid on top, and then you have an invariant point. In between, you have alpha plus liquid, and you have also beta plus liquid. And at the bottom, you have the mixture of the two solids, which is alpha plus beta. And whenever we look at each phases, like for example, I give you 1 point over here, okay, and you need to determine what will be the composition. It will actually depends on the phases that it exists. For example, if I put point at the bottom here, so you know that the phase is actually alpha plus beta, then the composition that you should report will be the composition of alpha and composition of beta. If let's say that I put a point over here in between of alpha plus liquid, then the composition that you need to report is actually composition of alpha and also composition of liquid. So the same case, you just drag the line, and then after that, when it intersect with the solidus line, you will get the C alpha. And if you drag the line until the liquidus line, you will get the composition of liquid. Okay, right. Okay, so this is actually what I've told you. Okay, if you look at these 3 points, A, B, and C, okay, so you know that for point A, it will exist as liquid form. Okay, so you only have one phase, then there will be, the composition of A is basically the same as the composition of the initial composition asked. So over here, maybe if I ask you what would be the composition of A, perhaps someone can answer that. Maybe I can call from list over here. Balkis Hanani, ada tak Balkis Hanani?
Yes, doctor.
Yes. So what would be the composition of A, roughly?
100% liquid.
That is actually, I think if I ask you the amount, maybe of course it's 100% liquid, but the composition,
Oh,
berapa tu?
55% of SN.
55% of tin. So since you know that it is actually 100% of liquid, then you just drag it down and then you just read it from here, roughly lah. So we get around 55% of tin, right? So good, right? So how about point B? Maybe I can ask Faris. Faris, Yani, Faris. Faris ada?
Yes, I'm here, doctor.
Yes. So Faris, so what will be the composition? What will be the phase first that you observe at point B? Dia dalam fasa apa tu? Point B, Faris.
Fasa liquid and I'm not sure.
So nampak tak dia tu B tu dia dekat dalam ni tau. Dia dalam region ni. Dalam triangle ni. Nampak tak?
Nampak.
So
So
dia
alpha plus
yang dalam triangle tu apa? Fasa apa? What will be the phase? What is the phase?
Alpha plus liquid.
Faris tak clear kot line. Okay. So it is actually a phase of alpha plus liquid. Okay. So meaning that when you have a mixture of phases, alpha plus liquid, then the composition must be, I think, two as well, alpha and also liquid. So if Faris ada masalah internet sedikit sebab pun pakai phone. Gary Tian.
Yes, doctor.
Okay, Gary.
Yes,
So,
I'm here.
what would be the first phase that you can read? Maybe since we know that this alpha plus liquid, then what would be the composition of alpha? Maybe if you, roughly, berapa?
40% tin.
You just
40% tin.
50%.
Yeah.
Okay. So basically, saya tak boleh contoh. Plus liquid, and you have solid line of alpha on your left hand side. Nampak tak ni? And then you have line. So in order to read alpha first, saya tak boleh nak draw line. Line over here, then with solidus line of alpha. I don't know, maybe 16 or 17. Okay, okay. So you just Okay, so can you guys hear me back? Very sorry, suddenly I was kicked out. Okay, all right, thanks. So let me share again the slides. Oh.
Binary eutectic system.
Okay, where is it? Right, so can see, Okay, so back to the question. I guess just now I have mentioned about point B and then point C. So point C now we know that it is actually the phase of alpha plus beta. Okay, so what will be the composition of alpha and beta? Maybe you can ask Mardiana Zubir, ada tak? Mardiana tak ada.
Ya,
Ada?
ada.
Ada.
Ya.
So what is the composition?
Composition of the tin. 40%?
Untuk point C.
Oh, point C. For point C. 40%? Is it wrong?
Phase dia apa phase dia?
Oh, phase dia. Oh ya, phase dia alpha plus beta.
Okay, alpha plus beta. So kalau ada alpha plus beta means that you have to report the composition of alpha and also composition of beta. So dia bukan 100%, dia memang solid lah, but it is actually a mixture of solid, alpha and beta. Not the same as isomorphous because I told you for isomorphous, when it become alloys, solid tu dia akan jadi satu saja. But for eutectic system, when it solidify, it forms a two solid grains together. So sebab tu dia untuk point C tu walaupun dia dalam solid tapi dia solid alpha plus beta. So berapa? What is actually the composition of alpha and beta? If you read roughly lah.
Sekejap. It will be I don't think so.
Tak boleh baca? Boleh baca?
Tak boleh. Ayuh.
So point C tu, actually I told you, kalau kata kita dah nampak dia dekat alpha plus beta, so you just drag line. Saya tak boleh nak draw line dekat PDF ni. So
Okay.
I just guide you. Okay, so you just drag it until here, until the, nampak saya punya cursor mouse tu, nampak tak?
Nampak.
Okay, so you just draw a line until it intersect with this solidus line of alpha, and then after that you drag it down. So literally, if you read it, it's around 10% of tin for alpha.
Yeah.
Meanwhile, for beta, okay, so you just draw another line when it actually intersect with the beta, solidus of beta. So you drag it over here. So maybe around 1998 or 97 values lah. Okay, right. Boleh
Boleh.
Okay. So it is important. I think I have to make sure that you really understand how to read the phase diagram of eutectic, because after this you will see more complicated phase diagram lah. Okay. Right. So now we are going to look at the examples. So the previous examples that I've shown in the lecture notes probably on the phase composition and the mass fraction. But there's also another important values that I told you, I think last 2 weeks, which is actually on volume fraction. So we are going to look at the examples. So for point C, 40% of tin, 60% of lead alloy at 150. Question A, what will the phases present? B, what are the composition of phases present? C, mass fraction, and D, volume fraction. Okay. knowing that the density of lead and tin are 11.23 and 7.24 gram over centimeter cube respectively. So if you know apa tu the formula when you have density it means that mass over volume. Okay, so when you want to calculate apa tu volume, so you have to know what will be the mass and also the volume. Sorry, density. So we are going to talk about the density fraction and also the mass fraction. Then only you will get the volume fraction. Right. So this is actually the phase diagram. Question asked at 40% and 150. So 40% and 150, this is actually the point C. So the phase of course, it exists as alpha plus beta. Okay. Second question, okay, composition asked. Okay, so we know that it is at alpha and beta. Composition at alpha, it is actually around 10%. So drag line over here, we drag it here, 10%. And composition of beta, it is actually at around 98%. Right, settle. Question C is actually on the mass fraction. Okay, so when you look at the mass fraction, so the same concept will apply. You will actually assume this as a tie line and then you will make it as R and S. One half as R, another half is actually for S. So alpha, weight fraction of alpha. Alpha is actually located on your left hand side. So the opposite line of alpha is actually S lah. So alpha dekat sebelah kiri, and then the opposite line, line yang bertentangan adalah S. So what will be the S? So S is actually C beta minus with C naught. C beta is 98 minus with 40 over, okay, the length of the tie line. The length of C beta and also C alpha. So 98 minus with 10. Then you will get mass fraction of alpha is equal to 0.66. Meanwhile, for beta is located on your right hand side. So opposite line will be R. Opposite line will be R. So R is actually C naught minus with C alpha. C naught is 40 minus with 10 divided with the length of the tie line. 98 minus with 10. So you will get 0.34. Okay, understood? Quite easy. Okay, the first three questions. But the more tricky question will be this one. Okay, how to get the volume fraction. So as I told you, in order to get the volume fraction, you should know what will be the weight fraction and also the density fraction. Okay, so in order to calculate weight fraction, I think weight fraction we use a tie line formula. Meanwhile, for density fraction, you have to use a formula as well. So this is actually the formula. We have to actually calculate the density fraction of alpha and also the density fraction of beta. Okay. So the density of fraction of alpha can be calculated as follows. So the total, I think the total mass or the total density is equal to 100% divided with, okay, first the composition of alpha. So composition of alpha, okay, because the question is actually asked for density fraction of alpha. So composition of alpha is actually equals to 10. The remaining composition of lead will be 90%. So this can be easily calculated as 100 minus with 10, then you get 90. Okay, so it means that 10% of tin will be divided with the density of tin, 7.24, plus with 90%, the remaining will be 90% of lead over the density of lead. Okay, so if you calculate all these things together, you will get the density fraction of alpha equals to 10.64 gram over centimeter cube. Okay, so meanwhile for beta, okay, beta density fraction of beta, the same thing, 100% over composition of tin for beta over the composition of tin for beta. So composition of tin, just now we read from the phase diagram, it is equal to 98. Okay, so the remaining of lead will be 2%, because 100 minus with 98, you get 2%. So to calculate the density fraction, so you need to divide 98 divide by 7.24 plus with 2 over 11.23. Then if you calculate all together, you get the value is equals to 7.29 gram over centimeter cube. Right? So the most important thing in order to calculate the density fraction of alpha and density fractions of beta is the value, the composition of tin, alpha and beta. Over here, from the phase diagram, okay, sorry. On the phase diagram, we get composition of alpha is equals to 10% and also 98%. So these two values that you need to remember to be put over here. One for alpha, you put 10. Another one is 98. The remaining will be the subtract value. Okay, 90 and also 2. So the division must also correct. So if we actually look at the composition of alpha on the percentage of tin, so 10% is actually 10% for tin. Then the density must be divided with the values of the density of tin. Same goes to here. Okay, right. So once you get the two values, the density fraction, then only we can calculate the volume fraction. As I told you, in order to calculate the volume fraction, okay, because we know density is equal to mass over volume. So in order to calculate volume, then you have to find the, I think the values of maybe weight over density. So from this formula, okay, W alpha divided by rho alpha over W alpha over rho alpha plus W beta over rho beta. So from the earlier calculation, we get W alpha is equal to 0.66. So you divide with rho alpha, which is equals to 10.64 that you get just now. Then you divide with the following values: 0.66 over 10 over 10.66 plus with 0.34 over 7.29. And when you calculate these things together, you get the volume fractions of alpha is equal to 0.57. Meanwhile, the volume fractions of beta, you will get around 0.43. Okay, right. So is it clear? I guess this one maybe you should memorize lah. So if I told you to memorize, it means that these things is quite an important things lah. Normally, it's a popular question been asked in your test or in your exam. What will be the volume fraction? So if you don't know what's the formula, then probably you cannot get the answer, or the calculation will be entirely wrong. Maybe you assume that it would be for weight fraction and not for volume fraction. Okay? Ada soalan tak? So far? Is it okay? Is it clear? Any question? Any question so far? All right. Okay, so we are moving on to the microstructure of eutectic alloys. So in isomorphous system, we have seen the microstructure for equilibrium cooling and also non-equilibrium cooling. For eutectic alloys, we have a microstructure, but the microstructure will be at different range. You will have a different picture in the end. So the first one that we are going to look at is at the microstructure at around 0 to 2% of tin. This is in the case of this range, 0 until 2% of tin. 2%. 2% is somewhere here. This is actually, we can say, the points where the solidus line ends, around 2%. So before that, so if you have a point or a composition in between, then this will be the microstructure. Okay, so let's say that we have 1% of tin, 1% of tin. Okay, and you have at different temperature. We have one at 350, we have one at 325, and we have another one at 270, for example. Okay, so what will be the microstructure? Of course, at around 350, at 1% of tin, you have liquid composition. So the microstructure will be blank lah, tak ada apa-apa, kosong saja. So the composition will be equals to the composition initial. Let's say that over here I told you it's around 1% of tin, then you have a microstructure L that is equals to 1% of tin. Right. Moving on to the next one. Let's say that we have at around 325, okay, at 1% of tin. Then this is actually at inside this triangle. So you have alpha plus liquid phase. So the microstructure will be as follows. So you have a formation of grains of alpha, and also the outer part will be liquid. Okay. So the composition also, I think you can easily read it from the phase diagram. If you want to read composition of alpha, you just drag until the solidus line and you read the value. Same thing if you want to read the liquid composition, then you just drag until the liquidus line and you drag it down. Okay. But the most important thing is if you have alpha plus beta, this will be the microstructure. And finally, if you have 1% of tin at 270 or 280 degree temperature, you will actually see the phase is actually at alpha only. Okay, solely in alpha region. So when you have alpha, then you know that it will be 100% alpha solid. Then the formation of microcrystal will be a polymorph alpha formation. Okay, so composition will be equal to the composition initial. So this will be equals to 1%, let's say. So this microstructure in between 0 until 2% applies to composition equals or less than this range. Okay, so we move on to the next microstructure region. Okay, so this is basically in the case of a region between 2 until maybe over here is 18 lah, 18 or 19, 18 lah. So if you have a composition between 2 until 18% of tin, okay, at different temperature, then this is actually the microstructure. Let's say that 15%, 15% of tin, and then you have one at 350, you have another one at 280, you have also another one at 190, and finally at around 120. Okay, so we have like 4 points over here. First one at 350, it will actually exist as liquid. Okay, so microstructure is still the same, blank. Composition will be equals to the composition initial, 15% of tin. So at point E, okay, maybe at the temperature of 280, okay, so you have a region at alpha plus beta. So similar microstructure, you will have a formation of alpha grains, okay, alpha grains. With the outer part will be liquid. Composition of alpha and liquid can be easily read from the line that you drag. Over here, you drag until solidus line, you get C alpha, You drag it until here, until the liquid line, you get C liquid. Meanwhile, at point F, okay, at around 190 degree, okay, this is where the phase is actually alpha only. Then you have formation of polymorph, alpha polymorph. Okay, composition is equal to the composition initial, 15, for example. And then at point G, G you have a phase of alpha plus beta. So when you have alpha plus beta, then you know that it is actually solid, but it contains alpha and beta. So the microstructure will be the same as alpha polymorph, except that you will see there's a small grains of beta. Nampak ada bintik-bintik merah ni. Okay, so you will see that this is actually beta. And why beta is quite small? Because the composition of beta is not much. Okay, or sometimes we can call it as hypo eutectic, hypo eutectic region, where you have more alpha and less beta. Okay, so moving on to the next region for microstructure is when you have the composition equals to the eutectic composition. So just now I think we look at berapa tu tadi? 2 until 18%, somewhere here. We haven't discussed from 18.3 until berapa ni? 61.9. We haven't discussed at this range yet, but for this range, the microstructure that we are going to discuss is at composition of eutectic, which is at 61.9. So what would be the microstructure? So the possible microstructure that you can see is at point H and also point I. H is basically at liquid phase, and then I is actually at alpha plus beta. Okay, right. So what would be the microstructure? Microstructure for liquid, still the same. Liquid, you have blank image. Composition will be the same as composition as or initial. So it will be the composition of eutectic 61.9. Meanwhile, at the lower temperature, below than 183, below than 183, if you have 1 point over here, point I, it is at alpha plus beta phase. Then the microstructure that you will assume or you will get is actually a lamellar structure. So this is actually a lamellar structure of solid plus alpha. So lamellar, what does it mean by lamellar? Lamellar structure, it means that it has alternating phase or alternating structure. So you have maybe alpha beta arranged alternatingly. Okay, so still forming at polymorph. Okay, but you have alternating layer or lamellar structure. Okay, so the more explanation of lamellar structure can be seen as follows. This is actually the scanning electron microscope of eutectic structure of alpha plus beta at composition of eutectic. So this is actually the lamellar structure that you will see. Nampak macam bentuk kulit zebra ni. But this is actually the alpha plus beta region. Composition of alpha and beta are very different. Eutectic reaction involve redistribution of lead and also tin atoms by atomic diffusion. Simultaneous formation of alpha and beta phases results in a layered or lamellar microstructure that is known as eutectic structure. Okay. So in eutectic phase diagram, it is also important to know what does it mean by primary alpha and also primary beta. So primary alpha is a phase formed in the alpha plus liquid region. That you have like more alpha lah, more lead as compared to tin. Okay, so in this eutectic structure that includes a layer of alpha plus beta phases that is known as eutectic alpha and eutectic beta. Okay, is formed upon crossing the eutectic isotherms. Okay, right. And finally, I think we are going to look at the microstructure, okay, of a range in between 18.3 until 61.9. So what would be the microstructure? Let's say that the composition that I asked you is at 40% of tin, okay, and at a different temperature, 300, 220, okay, 180, and maybe 185, for example, and then another one is at 170, for example. Okay, so you have point J, K, L, and M. J still exists at liquid phase, then there's no microstructure, blind. Composition will be equal as composition initial, 40%. K is at liquid plus alpha. Okay, you still see the formation of small alpha grains. Point L, you will see that the formation of alpha grain will become bigger. Okay, point M, this actually at alpha plus beta. Okay, but what makes the difference? I think earlier that we look at maybe at around 2 until 18.3%. Okay, it forms a polymorph and then a small grain of beta. But now you will see that at point M, the microstructure will be the formation of lamellar structure and, okay, the formation of a bigger alpha grains that we call it as primary alpha. Okay, you have a lamellar structure as a background, ada lamellar structure berbelang-belang, and you have formation of primary alpha grain, quite big. It is not the same as at eutectic composition where you don't have any primary alpha over here. It's just lamellar structure. But in between 18.3 until 61.9, this is actually the microstructure. You have lamella and also primary alpha. Okay, right. So if I ask you another question, what will happen if, let's say, I ask you the microstructure at composition in between 61.9 until 99%, somewhere around here, this region. Okay, let's say 80% of tin, 80%, and we have maybe different points, assuming as if it is at 300 degree, 220, 185, and also 170. So what will be the microstructure? Anyone knows? Or anyone can answer? Muhammad Farhan ada tak? Farhan ada? Tak ada. Ada? Nampak on mic tu. Farhan, so kalau saya tanya, kalau dekat 80% tin, and then saya bagi temperature yang sama juga, 300, 220, 185 dengan 170. What will be the microstructure? Do you think that it will resemble almost the same as what we have seen just now?
Sama.
Sama. But what makes the difference? Apa perbezaan dia?
Dan dia yang ni beta plus liquid.
Okay.
Beta plus
So
liquid.
microstructure mungkin kalau you lukis tu lebih kurang sama, tapi yang membezakan dia adalah
Dia beta plus liquid. Ada
Okay, saya faham lah maksudnya. Kita nak cakap kat sini, okay, we know that at the region of 61.9 until 99%, you have more beta as compared to alpha. Microstructure will be almost the same as what we have seen just now. Nampak ada grain-grain ni semua, formation of this grain. But it will be no longer as alpha. It will be as beta. So katakanlah kat sini, kita dapat a microstructure, then the formation of the grain is actually the grain for beta. In fact, okay, for the solid that forms at alpha plus beta, at this region, it will show eutectic or lamellar structure, but it will be primary beta, no longer primary alpha. Okay, right. So I hope clear lah, because I'm not going to explain it in the notes. So the same theory of concept, you will see the same microstructure, except that right now we are looking at a composition of more beta, then it will be apa tu primary beta formation rather than alpha. Okay. So this is actually the electron microscope lah, that shows the formation of primary alpha or primary beta. You see the lamellar structure. A bigger grains of primary alpha can be seen over here. Okay, formation of primary alpha or the lamellar structure, I think I have explained it earlier. Okay, ni dia dah masuk bab yang lain. I guess maybe I would like to show you the definition of hypoeutectoid and hypereutectoid. Hypereutectic and hypoeutectic. Sekejap. Okay, all right. So all this microstructure we have seen just now, okay. And before we go to last examples, maybe we should understand what does it mean by hypoeutectic and also hypereutectic. Okay. Oops. Right. So hypoeutectic, okay, it means that the composition are those with a small percentage composition of beta and greater composition species of alpha in the eutectic composition. So the range for hypoeutectic range, it will be at around 18.3 to 61.8 or 61.9. So this is actually for hypoeutectic. Meanwhile, for hypereutectic, it will be at around 61.9 until 90, like over here, 97.8. This is actually for hypereutectoid. So what does it mean by hypo and hyper? The most easiest way to explain. So hypoeutectic, it means that you have more alpha, less beta. Hypereutectic, it means that you have more beta, less alpha, because we are looking at this region. Okay, so this region you have like more alpha lah, alpha grains, because it's near to alpha. And then for hypereutectic, you have more beta because it's closer to beta. More beta. This one is more alpha. Okay. So that is why over here, if I ask you the microstructure, you can see these two things resembles almost the same as hypoeutectic, except that this will be primary beta. And over here, you will see that this is actually primary alpha. Okay, right. So some basic definition of hypoeutectic and hypereutectic will be explained. Normally will be asked during exams or tests. So make sure that you understand what does it mean by hypo and hyper. The easiest way to memorize it is that hypo you have more alpha, less beta. Hyper you have more beta, less alpha. As simple as that lah. Okay. All right. So I think just last slide lah before we end our lecture today. Okay. So examples, I think the microstructure in between 18.3 until 61.9, we have discussed it literally, but in the same time, you can also calculate what will be the mass fraction over there. So the same rules will be applied. If you have a point over here, you have R and S. So you can actually calculate what we or see what will be the alpha value and also the liquid value. And from there, you can calculate various kinds of weight fractions. Either it will actually forms at W alpha and WL, or if it is in the phase of alpha plus beta, it will be W alpha and also W beta. Right. So any questions so far? Anything that you want to ask before we end our lecture today? Right. So I guess maybe for today, I will give you one quiz for you to understand the basic concept of eutectic system. Okay, so the quiz, no need to worry. I will post it today. Deadline will be tomorrow lah. I will give you ample time for you guys to understand and to do it. Okay, and probably later on, I will also post you another homework to draw the microstructure starting from the range of 0 until 2%, okay, and then 2% until 18.3%, microstructure at eutectic composition 61.9, and finally in between 18.3 until 61.9. So this, I think, homework, I will give you also ample time to do it until Friday. So you can draw it, but because I guess it has quite a few microstructure that you need to draw, maybe you need some time. Okay, but for today, I will post you the quiz 2. As I said, quiz 2, I will give you more time, okay, until tomorrow. So tomorrow, maybe before afternoon, you should submit it, and before our class. So before I end our lecture, this is actually the attendance for today. And if you have any other question, I will stay back. I will answer any of your question. Or if you don't have any question, I will adjourn the class today. Thank you very much for your kind attention, and hope to see you tomorrow. I will let you know what will be the time for tomorrow, because I still not have decided. But maybe around 5 lah. Okay. So thank you very much, guys, for your time. Hope to see you again tomorrow. So Assalamualaikum warahmatullahi wabarakatuh.
Good.
Yep, welcome.